There are lots and lots and lots of chemical compounds, and so they can be represented in different ways. One of the most concise ways to represent a compound is with a chemical formula. And the chemical formula is going to tell us which elements are in that compound and the relative numbers of atoms of each of those elements. And so how we do this is we use the element symbols, the 1 or 2 letter element symbols, and then we use some subscripts to indicate the numbers. So water has the formula H2O. So hydrogen, there's 2 hydrogen atoms, and oxygen. We don't write the 1 after that because it's not really necessary. If it was another number like 3, we'd write the 3. If there were 0 oxygens, then we wouldn't write the O at all. So we tend to leave out the 1s. Carbon tetrachloride, CCl4. You have to be a little careful when you look at these because you could say, well, there's 2 carbons there, right? And then that must be iodine. Well, that's actually a lowercase l. Lowercase l, capital I, and the number 1 can all look very similar, right? What's that? No context. No way to tell. Whatever you say, I'll say something else and you'll be wrong. What's that? That's a capital I. What's that? Lowercase l. That's my number 1. So when I handwrite, I try to make these look distinctive so that I don't confuse myself. Here, if this was 2 carbons and 4 iodines, it would be C2I4. And so we can safely assume that there's 1 carbon and that this must be Cl4. We can write different kinds of chemical formulas, empirical formulas, molecular formulas, and structural formulas, and they give us different sorts of information. An empirical formula, empirical means from experiment, just gives us relative numbers of atoms. It doesn't tell us how many atoms are actually in a molecule, it just gives us the lowest ratio. So, hydrogen peroxide has an empirical formula of HO. For every 1 hydrogen, there's 1 oxygen. That doesn't tell us, though, what's actually in a molecule of hydrogen peroxide. It just gives us the ratio. The actual molecule is H2O2. So it's got 2 oxygens and then 2 hydrogens. This is the lowest ratio. The molecular formula gives us the actual number of atoms. So what I wrote here, H2O2, that's the molecular formula for hydrogen peroxide. It's just an example. I don't expect you to remember that right now. So here we have a formula, C4H8. Is that an empirical formula? No. It's not an empirical formula because the subscripts are not in the lowest ratios, right? A fraction of 4 to 8 could be reduced to 1/2. We can look at 4 and 8 and say, well, we can factor a 4 out of each of those. There's different ways to think about it. But this can be simplified to the ratio CH2, where there's 1 carbon and 2 hydrogens. That's the ratio. It doesn't say, this is the empirical formula. It doesn't say how many atoms are in a molecule. This is the molecular formula. Here's another one, B2H6. It's a molecular formula. From this, we should be able to write its empirical formula by simplifying the subscripts. This is a ratio of 2 to 6. We can simplify that to 1 to 3. Here's that CCl4 again. I'm telling you that this is a molecular formula because it's in this thing about molecular formulas. Can that be simplified? No, it's already in its lowest ratio. That is also the empirical formula for that compound. An empirical formula is sometimes a molecular formula. We also have structural formulas, and these help us understand how those atoms are arranged. As we see this C4H8, it's like, well, how are all of those combined? We don't really understand from the formula. There's actually a couple of different ways those could be put together. Structural formula is going to tell us exactly how the atoms are attached to each other. Structural formulas can be drawn in a couple of different ways. Typically, we use a line to show a covalent bond, and we use the element symbols to indicate the atoms. A single line is for single bonds, a double line for double bonds, and a triple line for triple bonds. Which formula we use depends on how much we know. Sometimes we only know the empirical formula, so we can't do anything else. It also depends on how much we want to communicate. Structural formulas give the most information, but they can be rather tedious to type out into a computer. And they can take up a fair amount of space when you're writing them out by hand. And so we don't always need to convey that much information, so we might use a molecular formula instead. The empirical formula gives us the least amount of information. So this is something you should be able to do. Write the empirical formula for the compounds represented by the molecular formulas given here. So what is the empirical formula for C5H12? It is C5H12. The empirical formula has the lowest whole number ratio of the subscripts. 5 to 12 has no common factors other than 1. That doesn't help. How about Hg2Cl2? HgCl. This is showing a ratio of 2 mercury atoms to 2 chlorine atoms. It's the same ratio as 1 to 1, right? How about C2H4O2? CH2O. That making sense? We can also have models, and these are 3-dimensional things. You can actually have an actual physical model, or you can have an illustration of a model. Ball and stick models use balls and sticks to represent atoms and bonds. And typically we use the same colors to represent different elements so that we don't always have to be writing the letters in there. And you'll see that these are the colors that are used in your textbook, and they're pretty common. White for hydrogen, black for carbon, blue for nitrogen, red for oxygen. Those are very standard colors. You don't need to memorize those, but I'm just letting you know that's why water is always red and white in your book. So this is a ball and stick model. We can also have a space-filling model, which gives us a better picture of the real shape of the molecule and how it occupies space. Ball and stick model is easier to draw than this one. And then just for comparison, we have the structural formula and the molecular formula. So this is the formula, CH4. This shows how the atoms are connected. Doesn't give us any information about the 3-dimensional shape. This shows us that this is in the shape of a tetrahedron, and this space-filling model shows us there's not really all this open space in there. It's really more of a blob molecule. This table from your textbook just shows for several different compounds these different ways of representing them. Here we get to see some double bonds. The double bond is indicated with 2 lines. In the ball and stick model, that would be indicated with 2 sticks. We don't see the bonds in the space-filling model. This one has a triple bond in it. This is glucose. That's your blood sugar. And the formula C6H12O6, there's actually a whole bunch of sugars that have that same exact formula, and your body knows the difference between them. It has to do with exactly how all those atoms are connected to each other. So we can represent that this way in a ball and stick model. The nice thing about this is you can see what's on the other side. You can see that this hydrogen here is on the other side. When you make a space-filling model of something complicated like this, you can't see what's on the other side, right? So you can only see one side of it at a time. Any questions? We use all these different ways to represent molecules.